the code structure doesn't represent the intent and the business flows in the application. Very rarely this happens. And when it happens is because it's intentional, because we are structuring the architecture according to the business lines and according to the business flows. But most of the time, the structure of the architecture and the structure of the code is around technical requirements, technical needs, technical constraints, technical patterns. This is a problem when we bring AI into the mix, because once you bring AI agents, they don't have a memory, so what they see is what they understand. And even if they could see the whole project, which they can't for large projects because the context window is too small, but even if they could see the whole project, the information about intent is lost. So how do you deal with this? This was a problem for people, but it's now an even bigger problem because it's amplified by AI. This is what I want to tackle today. Welcome back to Think Design Work Smart. I'm Alex Bolbaka and I'm coming at you from the Mosaic Work Studios. And today I want to talk about how the best Superman is the one from Smallville. Wait, no, I think this is not what we are talking about, right? In fact, I want to talk about an article written by Ian Bull, published on February 26, 2026. It's called Things Not Pipes, Software Architecture in the Age of AI. And it makes a very interesting point regarding the difference between the code structure and the architecture structure and the intent of the code and what we need to take away from it and how AI changes this. So let's go through this. Over 20 years ago, I wrote a master's thesis about navigating software architectures. The central problem was simple: large code bases are hard to understand. New developers joining a project face a daunting ramp-up period. The relationship between modules, the hidden dependencies, the unwritten conventions, all of it lives in the heads of the people who build the system. I built tools using relational algebra to query code bases, extract their structure, and help people reason about the architecture without holding the entire thing in their heads. 2 decades later, we're facing the exact same problem, except now the new developer joining your codebase every morning is an AI agent, and it has no memory. Every session starts from zero. This changes everything about how we should think about software architecture. Let me pause here a little bit and mention one thing. I've tackled in the past this problem coming from a different perspective, and the perspective was the one of usability of software design. If you think about what usability is, it's a design paradigm. It's a desirable design quality, let's say, it's similar with the other ilities. And it has a few components. And one of them is called learnability. So how fast can you learn to do a task in a new system, in a system that you've just learned? And usability maps perfectly with this need, introducing a new developer in your code. And my argument from my thesis and the book that I published that's available on Limpub on usable software design has always been that you can structure the code in such a way as to increase usability of the software design, and that it has enormous economic advantage because you can add new people, existing developers make fewer mistakes, therefore fewer bugs, you get better flows and that go more smoothly, and so on. So there are a lot of different aspects to this. But, well, I was one person and I had a few friends also promoting this, so it didn't go very far. These things need to be taken over by big tech in order to make any change in the industry. And I really believe this is a fundamental change for good in the industry, because at heart, I'm a humanist. I want people to feel good at their jobs. And If do something that they like and do it in a way that it's fun or at least not annoying. And now we see that the same problem comes with AI agent. Of course, there are other ways of dealing with that. You need to add into context to the AI agent. You need to add diagrams, documents, or architecture decision records, test cases that serve as examples of usage for various parts of the code and for how business flows are meant to work, and so on. So there are ways of dealing with that, and one of them is intentionally moving towards usable design, usable software design. The other one is to have enough contextual information that you can pass in so that the agents are actually working on something useful, and then save not necessarily the memory as they push us, but rather create an artifact out of every session that you're doing with an agent, an artifact that you can then reuse in the next sessions. The memory is good and all, but if you change the agent, if the model changes, if you don't have access to the agent anymore, if you don't want to use the agents on certain parts of the code, then it gets muddy. You don't have that information anymore. So it's best to create artifacts that are actually useful and preserve them and maintain those. And when you use AI, you use those artifacts, and when you develop, you use those artifacts as well. It's just as simple as that. Now let's look at what his solution is, Jan's solution. The new starter who never learns. Matt Pocock recently made an argument that resonated deeply with me. AI imposes strange constraints on your code base, and most code bases aren't ready. The code base itself, far more than any prompt or configuration file, is the biggest influence on AI's output. If it's designed poorly, the AI can get feedback fast enough, can find what it needs, and can figure out how to test its changes. And let me stop here again. This makes me think that we'll need to restructure our architectures in a way that AI can help. So if you are going full AI native and say, okay, I don't care about optimizing for people anymore, I care about optimizing for people plus AI, then what you can get to is what I've talked about before in these videos, a new type of architecture where you structure your code in very small modules that fit into the context window of an AI agent, and that can have duplication between them, that are completely independent, they don't know about each other. But on each of those modules, you can work perfectly within the limitations of an AI assistant. And one example here, one natural split would be if you have a web application, just split based on routes and actions. So you could have one module that just does post to /users, another module that just does get /user/ID, and so on. It's as simple as that. And of course, you get duplication, you get more code, but is it such a complicated thing? Because let's say you have a bug in one of the things and it's spread throughout multiple modules. Well, with an AI agent, it's just a matter of paying for tokens to make that go away pretty quickly. Because you can do this in parallel with multiple agents and say, okay, we have this problem, search for this sign, or write a test on all of these modules that proves whether the bug exists or not. And for those where the bug exists, go and fix the bug. And that's it. That's all you need to do. His metaphor is apt. When an AI agent enters your codebase, it's like the protagonist of Memento. No prior context, no institutional memory, just a fresh pair of eyes and the mandate to do something useful. Just to explain here, institutional memory, we could define this as the memory of the people, the collective memory of the people working on the product. Sometimes it's inherited from people who left, but also left some memories after them because they taught part of what they know to other people. Some of it is just living memory. Unlike a human new starter who gradually builds a mental model over weeks and months, the AI will never accumulate that understanding. Tomorrow it starts over, next hour it starts over. In my thesis work, I studied how software architectures could be queried and navigated using formal methods. I used a tool called Grok, no, not that Grok, built on a relational calculus to extract and reason about the concrete architecture of real systems like PostgreSQL. One of the key insights was the gap between what Recall called the shared mental model of the system, the conceptual architecture that lives in developers' heads, and the actual dependency structure buried in the code. That gap is where confusion lives. It's where new developers get lost. AI agents live permanently in that gap. And this is a very important point. There's a difference between what we imagine, what we know is in the product, and how it's structured. Or you could say the other way around, the structure of the code does not reflect the intent of the architecture. It rarely does. You need to put a lot of effort to reflect your intent in the structure. Actually, I had recently a conversation with Claude because on this point. And the idea is that every representation has text and metatext. That's part of semiotics, the science of interpreting symbols, of how we understand the symbols. So you have text and metatext, right? In video, you have things like if you're watching a movie, right? There are scenes when characters talk and there is music and the scenes are switched and that creates the text. But the metatext is how the movie is kind of structured. What's the fabric? Is one scene more blue and the other more red, or things like that? Is a character always dressed in some kind of colors? There are a lot of things like that give you information that's not directly in the script or even necessarily in what's very obvious in the video. And then there are additional things like the way you switch scenes. Do you do a fade to black? Do you do a fade to white? Do you do a cross resolve? All of those have meaning. Each of these adds to the language of a movie. Same thing happens when you are reading books. There's the text and then there's the metatext. There are the things that are not really described in the text, but things that you imagine. And when more people imagine similar things, it means that there's some connection there. So you have some metatext. Same thing happens with code. If you just look at the code structure, you have text, which is the actual code, but then you have metatext. Comments would be metatext, but we can say that, okay, that's actually text, is part of the code. They are somewhere in the middle between that. But what about empty lines? If you add an empty line between statements, that is metatext. That is not something that is really taken into account as code, but is something that tells you, the reader, the coder, the person who interprets that code, it tells you some more information. And it turns out that AI agents completely ignore metatext. And that can be important. And that's just the first level. It's just the smallest level of extra information that you can get from code. Before we go to the next levels, which are much more high level, much more complicated, like is that business process, how is it distributed within the code? That's completely metatext. or the share mental model of the system. So yeah, I think we'll need more studies in semiotics of code, semiotics of software architecture in order to get this right with AI agents, because a lot of things are hidden. And the problem is that the agents ignore most of this, and we don't. Even if you don't think you take that into account, you automatically take that into account. Trust me on that. We can make some experiments. What my thesis got right accidentally. When I was working on architectural recovery and navigation 25 years ago, the motivation was human comprehension. How do you help a developer understand a million-line code base? How do you answer questions like which subsystems does this component actually depend on? Or are there architectural violations where module A reaches into the internals of module B? The approach I took was to model code bases as sets of relations, function calls, containment hierarchies, file structures, type references, and then query those relations to recover architectural structure. We could ask, show me every function in subsystem X that calls a function in subsystem Y. Show me the actual dependency graph between high-level components. Show me where the concrete architecture diverges from the conceptual one. This was useful for humans, but it turns out it's even more useful as a design philosophy for AI. The core principle is the same. The structure of your system should be discoverable from the outside without requiring you to read every line of code inside. Yeah, wouldn't that be nice? If you have to trace through implementation details to understand what a component does, your architecture has failed, whether the reader is a junior developer in 2002 or a language model in 2026. Now, I can almost hear C++ developers that I know screaming at this, because no, everything needs to be, it's in the details. Everything is in the details. There are systems and systems, okay? So if you focus on extreme performance optimization, then this makes less sense, because you need to structure around what the CPU needs and around the technical constraints more than you need to structure around the understandability constraints. But for 80, perhaps 90% of the code, that's precisely what we need. Deep modules and the return of old ideas. Pocock advocates for what John Austerhout calls deep modules in a philosophy of software design. We discussed about the philosophy of software design before, so if you want to learn more about that, watch the related video, which I probably won't add to this video, but you can find it on our channel. These are components with simple interfaces hiding substantial implementation complexity. Rather than a web of tiny shallow modules that all import from each other freely, you organize your code base into substantial chunks with clear boundaries. The interface sits at the top, the implementation is behind the wall. If the tests pass, you don't need to look inside. Yeah, modularity. And you see, another type of modularity. But what I would argue is that we need to go even further and to keep these completely independent. This is not a new idea. This is encapsulation. This is information hiding. This is Parnas, 1972. This is what every software engineering textbook has been saying for half a century. And we haven't done almost at any point ever. There are so few projects that are actually modular that it kind of hurts. But here's why it matters more now. Where a human developer works in a massive database, they can compensate. They build up context over time. They learn the tribal knowledge. I like this, tribal knowledge. That's true. That's true. We should also have some conversations about anthropology of software teams. That would be interesting as well. They know that this module secretly depends on that database table being in a particular state, even though nothing in the interface says so. And by the way, there is a concept called screaming architecture, where the architecture should scream what it's doing instead of you needing to search into the architecture to figure out what it's doing. And me, and along with a few friends, we've also explored these ideas of writing code that is bug-free, in the sense that it's virtually impossible to introduce an error when you're using something that exists. So for example, this module secretly depends on the database table being in a particular state. This should be part of the interface somehow, okay? And then you need to get creative and figure out how to make this. But ideally, you should not be able to even call this without having the database table being in that particular state. One way to do that is to chain calls. So you call a class that's kind of like a builder, right? Or it's actually a strategy pattern, or you can see it as a null object pattern. So you have this strategy, this class that you call and say, okay, first step of the process, check database is in the right state. And only if the database is in the right state, it will return you an object that you can use to do the next step. Otherwise, it will give you an object that you cannot use for the next step. And that would be a way to avoid that. Interesting thought, right? So there are all kinds of patterns that we can use for that make obvious these types of hidden assumptions. But you don't get to implement those by default. You need to design them into your system. You need to actually think about the design of your system to capture those. And unfortunately, that's not usually the case. AI can't compensate. It takes your architecture at face value, and if your architecture is lying, if the interfaces don't tell the truth about what the modules do, if there are hidden couplings and undocumented side effects, then the AI will produce code that looks correct locally, but breaks things in ways nobody anticipated. Yep. Sinks, not pipes. This brings me to what I think is the most important architectural principle for the AI era. Build components that are sinks, not pipes. A pipe is a component that does its work and then triggers something else. It writes to a database, which fires a trigger, which sends a notification, which enqueues a job, which updates another system. You understand what a pipe does, you have to follow the entire chain. You have to crack open every component downstream and trace the cascade of side effects, right? I have a few comments, but let's read more and then I'll come back. A sink is a component that receives input, does its work, and stops. Its effects are contained. You can describe what it does without reference to anything else in the system. You can treat it as a black box. True, although where I'm having some issues is where you have a multi-step workflow. And even if you implement each step separately, which is a good idea, you still need to link those steps somehow, like transactional behavior, but not only transactional behavior. It can be completely non-transactional, but just a business process. When AI is writing or modifying code, this distinction becomes critical. If your system is built from pipes where every action triggers a cascade of side effects rippling through the system, then the AI must understand the entire chain to make a safe change. It has to know that modifying the return value of this function will affect the database trigger, that will affect the notification service, that will affect the job queue. That's an enormous amount of context for an agent to hold it. It's exactly the kind of implicit coupling that makes code bases fragile. It's a higher level of connaissance, right? And we want to have lower levels of connaissance. And if you don't know what connaissance is, there's a video for that. If your components are sinks, the AI can reason about them in isolation. It can read the interface, understand the contract, write or modify the implementation, run the tests, and move on. The blast radius of any change is contained within the module boundary. Low coupling, high cohesion, but this time we mean it. We've been teaching low coupling and high cohesion since the 1970s. In practice, most code bases have drifted far from this idea. Yeah, and connaissance is the higher level concept for low coupling and high cohesion. And I think it's better for this particular issue than talking about low coupling, high cohesion. It's easy to justify quick cross-module import. It's easy to let the utility function accumulate dependencies. It's easy to let the boundaries blur when you're shipping fast. And by the way, you can avoid that by writing architectural tests that prevent you from doing exactly this. ArchUnit, other tools like that. But when AI is your primary code author, and increasingly it is, the cost of that drift compounds rapidly. Every hidden dependency is a potential source of hallucinated behavior. Every side effect is a gap in the AI's understanding. Every tightly coupled module is a place where a change in one corner of the system breaks something in another corner, and the AI has no way to predict it. In my thesis, I use relational queries to identify exactly these kinds of architectural violations in PostgreSQL. We could find places where the actual dependency structure diverged from the intended architecture, where modules that were supposed to be independent had grown hidden connections. Back then, this was useful for maintenance and comprehension. Now it's essential for AI reliability. Right, you can also use tools like ndepends, if I remember correctly. There are tools that map your dependencies, although they don't map. This is much more comprehensive because it looks also at database triggers and so on, as far as I understand. But the best tool I know for this is architectural tests by far. The principle is straightforward. If a module's behavior depends on state or side effects that are invisible in its interface, your code is not AI ready. If understanding what a function does requires tracing through 3 other systems, your code base is not AI ready. If your tests only verify isolated units but never exercise the actual integration path, your code base is not AI ready. Right. You need to give the right information at the right level of abstraction to AI system. That's basically it. Progressive disclosure of complexity. Oh, I like that. That's exactly what I think I mean. I mean, we are talking about levels of abstraction, but that's basically it. So when you look at the book, you can look at chapters, you can look at sections inside the chapter, you can look at pages, you can look at paragraphs, you can look at sentences, you can look at words. All these levels of abstractions are absolutely important to understand the whole. And some of those give meta text information, some of them give textual information. And they are both important, and the same happens with code. So I like where this is going, but let's see. One concept for Pocock's talk that maps beautifully onto my earlier research is progressive disclosure of complexity. In a well-designed code base, the AI or a human should be able to understand the system at increasing levels of detail. At the top level, you see a handful of well-named services with clear interfaces. If you need more detail, you look at the types and contracts those services expose. Only if you need to modify the implementation do you look inside. And by the way, this is what clean code is trying to do, and many people are criticizing it for doing precisely that and saying, yeah, but I need to read through the whole code in order to know what to change. No, you need to structure your code at different levels of abstraction, and when you make changes or fixes, do them at the right level of abstraction. And if you need to touch multiple levels of abstraction, you do that incrementally. First a lower level or a higher level and move on. It's something that I never really understood as a critique. Like I'm reading this function, but I don't know precisely what everything in this function does. I don't need to know everything that this function does. I just need to know that now I have 4 steps in a flow and I need to add a 5th. That's the first thing that I do. And then I implement the 5th step. I assume everything else is working correctly, and I implement that step, and then I test it together and make sure that it works together. It's incremental thinking, as simple as that. I never understood this argument. Maybe if you are one of the people who believes in this argument, well, why? Let me know in the comments. This is essentially what my thesis tooling did, but through queries rather than file system conventions. We would start with a high-level subsystem view of PostgreSQL, parser, optimizer, executor, storage, and then drill down into the relational structure of each component. The architecture was navigable because we could move between levels of abstraction without losing context, obviously, yeah. For AI agent, this has to be baked into the file system and the code itself. The directory structure should reflect the conceptual architecture. The public interfaces should be obvious and well typed. The implementation details should be behind clear boundaries. When an AI agent explores your code, you should be able to build a working mental model from the outside in, just as my thesis tools allowed human analysts to do 2 decades ago. Okay, so I agree that this would be the ideal. Now, first thing, it's funny and ironic that we're discussing about this in the context of making the job easier for AI and not making the job easier for people, which is what usable software design was trying to do. But that's how this industry works. I made my peace with that a long time ago. The other thing that I want to discuss here is that there are additional things you can bring into the mix. I've seen tools now that take the abstract syntax tree of the whole code, bake it into a database and allow agents to interrogate that database. And when the code changes, the database gets updated and so on. So that's one point. You can bring that into the mix, which means that you are working at a lower level of abstraction, the abstract syntax tree, rather than at the high level of abstraction. However, this does not tell you everything about the dependencies between different parts of the code that are outside of the code. I can tell you a lot about the code. I guess you can still miss a few things because there are some, for example, temporal dependencies. You need to call this before that. That's not easy to see in an abstract syntax tree representation. But the externalized dependencies are also unclear. If you need a trigger from a database when something happens in order to do something else, that's another thing. Or if you need an external thing like a cron job. So that's part of it. The other part of it is architecture documentation, because as much as I'd like to structure the code to cleanly represent the intent of the architecture, my fear is that this is only possible up to a certain moment. And this intuition comes from another point, which is if you try to post on social media sarcasm, people don't get it, right? It's a type of meta text that doesn't transmit well simply with text. So I believe we need meta text in addition to text, and probably something else like documentation in order to make the architecture comprehensible for people and for AI. I'm a people first kind of person, so for people first. But this doesn't mean that we cannot do a lot more and a lot better than what we've done until now. I think there's a lot of room for improvement, taking into account these ideas of usable software design, of screaming architecture, of writing code that is impossible to get wrong or very unlikely to get wrong. And yeah, I think we can do a lot more, but it's not really, I'm not sure we can do only with text, only with structure. But there are many things you can do. So for example, in your APIs, you could have custom types for everything. Let me ask you a question. Should password be a type or a string? Right? Normally, the usual representation is a string. But is it a string? I would argue that it's a constrained string. It's a constrained string because a password has certain requirements for security. So presumably you wouldn't want to load it into memory as plain text. You would want to keep it in memory only as a hash or only as a encrypted value. It has some limitations in terms of what characters can be there, but in terms of minimum length. So why is it not a type in your system and why is it a string? This is just a very basic question, right? We can imagine a lot more. So now imagine taking all the concepts from your code and encoding them into types that then both people and AI can understand. By the way, part of the usable software design code is a thesis for constraint types, where I argued that it would be much, much better if we had ways to take a type and say, I want everything from string, except the string needs to be minimum 10 characters long, and you cannot clone it, you cannot copy it, you cannot get a substring, and so on. So basically restricting the base class methods that are implementing in the derived class, and not only adding more constraints. So this would make a lot of sense. The 25-year echo. It's a strange feeling to look back at work from 25 years ago and realize it's more relevant today than it was then. The problem of studying architectural comprehension, dependency management, the gap between intent and the actual structure were real problems in 2002, but they were human scale problems. Developers could work around them with time, experience, and good communication. Now those same problems are machine scale problems. AI agents are hitting the same walls the new developers hit, but they are hitting them hundreds of times a day. No ability to accumulate wisdom between sessions. The architectural sins that a human team could tolerate, the hidden coupling, the undocumented side effects, the modules that only make sense if you know the history, are fatal to AI-assisted development. The answer isn't new, it's the same answer it's always been. Well-defined module boundaries, clear interfaces, minimal side effects, high cohesion within modules, low coupling between them. The only thing that's changed is the cost of getting it wrong. Yeah, so there are very few new things in software design and software architecture. In fact, most principles are very old. If your code base is a tangled web of shallow modules with implicit dependencies and cascading side effects, the no prompt engineering agent framework AI module, however capable, will save you. The architecture is the prompt. The structure of your code is the most important instruction you give to the AI. And if you get the architecture right, the modules with honest interfaces, components that are sinks rather than pipes, a file system that reflects your conceptual model, then AI becomes genuinely powerful. Not because the AI is smarter, but because your code base is finally telling the truth about itself. Let me just point to another thing, that maybe the file system is not the best way to express architecture, and maybe we need some kind of a graph system. But I talked a lot today, so I won't go into this a lot more. If you want to learn more, let me know in the comments. That's what good software architecture has always been about. We just have a much better reason to care about it now. So what have we learned? We learned that there's text and meta text. We learned that there's the structure that exists in the collective minds of developers working in a team, and there's the structure that is actually on disk in the code. And we've learned that AI assistants ignore meta text and only know the structure that is in the code. And what this tells us is that we need to compensate for those things, on one hand, by making our architectures to reflect better the intent, and second, I don't think we'll get rid of documentation like diagrams, architecture decision records, architectural tests, unit and feature-based tests, and probably some other types of representations. So there's a lot of work to do, and we might end up with a completely different structure for code. Maybe a graph-based structure, maybe based on queryable structure rather than on flat files and trees of files. Who knows? But no matter what we will be doing, we'll have modules, we'll have levels of abstraction, we'll need to have some kind of organization that goes on the principles of divide and conquer and separate high level from details and have multiple levels in between. I don't think we can get rid of those, no matter how much AI we throw at the problem. And if you want to learn more about any of these topics, we have some amazing learning programs for you. AI-powered software engineering, AI-enhanced software microservices architecture, from developer to architect, that is now using AI assistants as well, where you learn how to build architectures that are following these types of principles. And we actually practice. We do architecture, we discuss about the results, we identify trade-offs. That's what our courses are about, giving you real skills that you can use the next day in production. With this being said, let me know in the comments what you think about all this. Have you noticed limitations in using AI assistants in your code? Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.